Hello everyone. So now with some very detailed, nice technical presentations, I'm more giving you a more holistic view on the airborne wind energy system and its connection with the energy system itself. So what is the need of that? What is the need of looking at the bigger picture, and how do we get more insights from this? So yeah, as Roland understood, I'm Rishikesh Joshi. I'm a PhD researcher at Dell with under supervision of Dr. Roland Schmel and Sir Dominic Ponchesi. So today we present our work titled Towards Optimum System Design of Ground Chain Airborne Wind Energy Systems. So now for successful diffusion of airborne wind energy in the energy system, what we need to understand that the technology development should go hand in hand with the requirements dictated by the market. And every different market will have will demand basically different requirements, and we need to design different types of systems and system sizes catering to those particular markets. So the four factors which influence the system design are the available wind resource at for a particular market scenario, the performance of the system that you employ on that market, the cost of the system, and the value that can be derived by deploying that system in that market. So the wind resource and the value derivation are market dependent, whereas the technology and the cost, the performance and the cost are technology dependent. Now, how do we basically integrate all these aspects into a system design framework? So what we do? So this is the overview of the framework that we are building. And on the top left, you see basically the key system design parameters to which all the models in the framework are basically parametric to. So that consists of the high-level parameters of the kite, for example, the kite wing area, the aspect ratio, the aerodynamic concept, CLCD, and for tether, it's the maximum tether force, tether diameter. For the ground station, it will be generator-related characteristics. So I do not focus more on the aerodynamic and structural evaluation of the kite itself, but I take the pre-evaluated results as a starting point to move ahead. So for the kite mass scaling, we have a data-driven model, which is basically trained using the mass data obtained from company prototypes and projected data, and also literature. So it's basically a nonlinear function of wing area, aspect ratio, and the maximum tether force it can hold. The power computation model is a quasi-steady model. I will tell you about it in the next few slides. Then the other type of inputs is the site and project data. The two key inputs within that is the wind resource and the energy price mechanism. And basically the wind resource input to the power computation model leads to the energy profile of the particular system that we defined here. The wind resource characterization also includes vertical wind shear profile. And so we are also developing a parametric cost model, which is basically modeling the key scaling functions of the main factors of the kite, tether, and the ground station. I will tell a bit about this also at the end. And so up to this, using this toolchain, we can basically evaluate the levelized cost of electricity of a particular system that we define. And levelized cost of electricity is a standard design metric, also known as LCOE. But we also have a value model within it. So basically that is connected to the market side of things. So how does the energy price change, for example, and demand matching, and we also plan to extend it to calculate environmental impact, to something which was shown yesterday, an LCA model. So basically you can compare two systems, not just on LCOE, but metrics beyond LCOE that we can basically are open to define the value model. And so this framework can be implemented as an optimization framework based on chosen metric. Basically, you can find suitable designs, suitable design choices, design sizes, system sizes, which can cater for this particular defined scenario. This can also be used to do sensitivity analysis to identify which factors actually influence the final metric. So which of these factors are contributing more in the final, let's say, what market needs. And then the key question, so what are the kind of models that you choose for such a framework, right? So we know no model can be 100% accurate. Every model tries to model certain aspect in higher fidelity, whereas then it has more assumptions in the other aspects. So the key is to choose, of course, the simplest models, but which capture the critical interdependencies between the whole system. And so my view is basically the trade-off between the accuracy and specific aspects. So basically the holistic behavior. So we are developing a fast for computation model for this. It's basically a quasi-steady model in which we discretize the real-out length into number of length elements, and we assign each length element with a single steady state, eventually leading to a quasi-steady simulation. So this tries to capture the critical physical aspects during the operation of the ground gen system, so reel out, reel in, and the physical aspects of centripetal acceleration, gravity, etc. The model is implemented as an optimization problem with an objective of maximizing the electrical cycle average for every wind speed, subject to multiple physical constraints, but basically finding out the operational set points for each wind speeds, that is the reel out length, operating lift coefficient during the cycle, average pattern elevation, cone angle, starting pattern radius, some ground station related parameters, that is the reel-in speed. So constraints are like your winch can only maybe have a certain maximum wind speed, so such constraints. And yeah, so these are some sample simulation results using the model. So this system specifications are tuned for the Ampix AP3 prototype. So the wing area of 12 meters square and some other parameters. So one key thing to note here is the generator size. So even though the cycle average rated is 150, you need almost 450 kilowatt to reach that rated at desired wind speed. So I'll show that some details about it later. And in blue is the model vertical wind profile used. For reference, I also added empirical data-based wind shear profile. So the yellow one is an offshore location in the Netherlands. The red one is an onshore location in the Netherlands. And a preliminary comparison of the power curve. So there's the black dots are the simulation results obtained from Ampix. This is the ideal Lloyd, which basically now we are trying to go in somewhere in between, but keep the speed of computation high so that we can do some sensitivity analysis. So maybe I won't go into the details, but these are some simulation results. On the top left, you see a cycle power representation. So in red is the reel out power, mechanical reel out power, and in blue is the electrical for rated wind speed, which is 16 meters per second. These are again the mechanical reel out power, electrical. The one in violet is the electrical cycle average, which is basically we cap it at 150 kilowatt, which was the required rated electrical power. But maybe we can come into this details later on the questions if you have any. Yeah, so this is one of the important slides which I wanted to show. So what does the model do? Like the capability of model is to do fast sensitivity analysis based on certain key parameters of the system, which allows us to see how much impact a certain aspect can have on the final performance. And this only is, I would say, a partial picture, because this is an impact on the power. But then if you couple this to energy and the cost, then if you look at the final impact on the LCOE of the system, then you know which factor is actually more important, and then basically that would drive more innovation in that aspect. For example, it's obvious that the CL will have more impact, so definitely, but still then you would know how much more gain in CL in the end will give you how much gain in the LCOE metric. So that's the trade-off here. And this is the variation with the maximum tether force, so basically which tether, how strong the tether is, and this generator size variation. Yeah. So the green, so the blue line, the 2.1 is basically a ratio between the cycle power and the generator size. So the generator size which I showed you earlier was 450 kilowatts. But if you use a 300 kilowatt generator, basically the reel out power cannot exceed more than 300 kilowatt, and hence the cycle average in the end cannot be more than around 130 kilowatts. So then this shows you how much the generator is actually oversized to only produce 150 kilowatts of of cycle power. So this coupled with the cost trade-off will, I think, again give more insights, but I don't have the results for that yet. But yes, I think so. What we are doing, we are in the process of building this integrated framework, and then trying to integrate the already individually published and our work together in such a framework. And the colors basically show approximate readiness levels of each aspect in our framework. And one thing which I would like to point out is about the cost model that we are developing. So this is also an advertisement because we are collecting data from the industry, and we'll be starting that soon. Me and Filippo, who's also here, are leading this activity, which is kind of the backbone for this cost model. And we are going to do this through the IEA Task 48 on airborne wind, and through Airborne Wind Europe. So yes, if you have any inputs regarding any of these aspects, you have suggestions on what are the things that you think are important to go into more detail, I think I'm really happy to hear about those. And yeah, this was my presentation. Thank you.
Thank you, Lucia. Are there any questions?
Thanks, yeah. Really interesting, and also sort of relating to the Task 48 work that's being done there. We yesterday saw a presentation where I was looking at sort of the different sites, taking as an example Germany and the different sites and evaluation there. Would this model be able to evaluate how much it would cost per kilowatt or something to run wind energy in different sites, etc.?
Yeah, so ideally indeed, like since this model is basically intended for such fast computations, and you can deploy it on much, let's say, easily, and adapt to different kinds of such studies. Definitely it can be coupled to that kind of study. Actually, there will be a presentation by Hira later today on a similar aspect in which we use the outputs of this model as an input to
Cool, thanks.
Thank you, Rishi, for that nice presentation. Basically the model was somewhat dependent on some tuning parameters, right, which were based on what MPIX did in the past.
Yes.
So if you would want to use the model on a different system, like how hard would that be?
So by different system, do you mean a different concept like soft wind or?
For example.
Yeah, I mean, I guess the key parameters here are the wing area, aspect ratio, CL max, but then these can be obtained maybe in a different way for soft wings. For example, the mass, the tether is okay, we can model the same way. But I guess the difference there is more on the transition phase and the reeling phase, because then we'll have to add it differently. Because for this particular fixed wing system, what I assume is the kite can easily glide back to its starting point, right? But the soft wings have a little bit slower transition phase and then a reeling phase. So that needs to be done for soft wing system. But for fixed wing systems, basically it's easy to evaluate. That's the whole idea, to explore the vast design space, and you can narrow down on any choice.
Yeah, so this would also work for another type of fixed wing kite. The scaling still would probably apply.
Yes, so for another types, if you ask about different concepts, I think the main impact would be on the mass. So for example, if you use, for example, you are now looking more into the box wing kite craft type kite. So I guess if you have more data about the scaling of the mass of that kite, then it will be valid.
Okay, thank you.
Just the Lloyd there is just for the real out.
Yes.
Any other question? Yeah, I think as part of your publication there is a mass scaling model, which is kind of tailored to MPIX.
Yes.
And of course it's a very specific aircraft configuration, but I'm sure that this can be somehow also, let's say, extended to other configurations. But for this we need more of these prototypes.
Yeah.
Any other questions? Otherwise, no. Thank you again, Rishi.